The first law tells us which processes are permissible, those that conserve energy. It does not tell us which of them actually happen. A cup of tea left on a desk goes cold, but a cold cup never draws heat back out of the room and reheats itself. Yet energy would be conserved either way. To run the process backwards, you need a kettle, and the kettle has to be plugged into the socket. The reverse direction must be driven by external work. The second law supplies what is missing. A spontaneous process is one that proceeds without being driven by external work. And the second law tells us which processes these are. In this chapter, we state the second law, define entropy S, and verify that ds is an exact differential, or equivalently, entropy is a state function. We then connect entropy to experiment through heat capacities, fix its absolute scale using the third law, then finally apply it to the Carnot cycle, where it places a ceiling on the efficiency of every heat engine, the question that drove the subject during the Industrial Revolution. The first law introduces a state function internal energy U, by combining two path functions, heat Q and work W. The second law introduces another state function, S, entropy. The second law can be stated as, a spontaneous process in an isolated system is accompanied by an increase in entropy. Note this does not mean entropy of the system must increase, because it could decrease provided that entropy of surrounding is an even bigger increase. We stated the second law in words, but we haven't defined what entropy is and haven't written down a math expression for it. So let's do that now. The most precise statement of the second law is the Clausius inequality. ds is greater than or equal to d bar q over t, where ds means entropy increase of the system, and the equality holds for reversible process, where it serves as a definition of entropy, which is heat added reversibly at temperature T. Analogous to work done reversibly at mechanical equilibrium, reversible heat transfer occurs at thermal equilibrium. The Clausius inequality clearly implies for an isolated system, such as the whole universe, we have ds is greater than or equal to 0. Entropy is a state function, so we have integral around the closed path ds equals to integral around the closed path d bar q reversible over t equal to 0, and the integral around the closed path d bar q over t is less than or equal to 0. Thus the second law also relates a path function to a state function. However, it is not obvious at all why dividing reversible incremental heat transfer by temperature converts it into an exact differential. So let's look at this more closely. We now show entropy is a state function in the case of an ideal gas. Turns out, even though we wrote U equals to U of V and T, the internal energy is actually just a function of temperature for ideal gas. So we have du equals to Cv of T dt, where Cv is the constant volume heat capacity. We now consider the first law for reversible process. du equals to d bar q reversible plus d bar w reversible, and using reversible work, we have d bar q reversible minus pdv. Then we combine the two equations and rearrange yields d bar q reversible equals to Cv of T dt plus pdv. Then divide by T on both sides gives the expression on the screen. Notice that the left-hand side is the definition of entropy. So we have ds equals to Cv of T over T into dt plus nr over V into dV, where we have used the ideal gas law Pv equals to nRT. Clearly we have ds equals to partial s partial t at constant V dt plus partial s partial V at constant t dV. Then equating the coefficients yields partial s partial t at constant V equals to Cv of T over T, and also partial s over partial V at constant t equals to nr over V. Then clearly the mixed second derivatives from both sides vanish. Therefore ds is indeed an exact differential in the case of a mole of monatomic ideal gas, and entropy is a state function for an ideal gas. We have shown this in the case of an ideal gas, but entropy is a state function more generally for any arbitrary material. Furthermore, you can show d bar q reversible is not an exact differential using similar method. We now make a connection to experiment. We talked about how to predict internal energy and enthalpy change for a given temperature range using heat capacities. Now we talk about how to use heat capacities to calculate entropy change for a given temperature range. Let's consider constant volume first, and from initial state point Vt1 to a final state Vt2. So we have the integral from Vt1 to Vt2 ds equals to the integral from Vt1 to Vt2 dq bar reversible at constant volume over t, which is the same integral over du over t, which is the same integral over partial u partial t at constant v into dt over t, which is the same integral of cv of t dt over t. Thus, we have the entropy at final state point Vt2 equals to the entropy at initial state point Vt1 plus the integral from T1 to T2 Cv of t dt over t. And similarly for constant pressure, we have S of P and T2 equals to S of P and T1 plus the integral from T1 to T2 Cp of t dt over t. These results hold even for non-reversible process and non-ideal gas, since entropy is a state function. Energy and enthalpy do not have absolute scale, as the first law never actually defined U, but it is written in terms of differences delta U or du. However, entropy do have an absolute scale, and this scale is provided by the third law of thermodynamics, which states entropy of all crystalline substance goes to zero as temperature goes to zero. And since we have equations that gives us temperature dependence of entropy, provided that we have the heat capacities at the temperature range, we can calculate the absolute entropy for any crystal. Now let's show the entropy change for any closed cycle is zero and make a connection to the applications to heat engines. Consider a Carnot cycle, which is made of 4 individual processes. So the Carnot cycle consists of 1. Isothermal reversible expansion from T2 V1 to T2 V3, then adiabatic reversible expansion from T2 V3 to T1 V4. Then is followed by isothermal reversible compression from T1 V4 to T1 V2. Then finally, we have adiabatic reversible compression from T1 V2 to T2 V1, which ends up where we started, i.e. a closed cycle. We can first check whether internal energy change is zero for this process. Clearly, isothermal processes do not change energy, and the two adiabatic processes gives internal energy change of delta U2 equals to Cv into T1 minus T2 equals to minus delta U3. Thus, internal energy change does indeed vanish for this cycle. Now, entropy change. Clearly, reversible adiabatic processes do not change entropy, so we only need to look at entropy change for isothermal reversible process, which is in general delta S equals to integral from Tv1 to Tv2 d bar q over t equals to q over t. But with no heat transfer for isothermal reversible expansion from the last chapter, thus entropy change for an isothermal reversible expansion is delta S equals to nr log V2 over V1. Subtly, although we have derived this by considering a reversible expansion, this expression holds more generally for non-reversible isothermal expansion because entropy is a state function. Thus, for process 1 and 3 in the Carnot cycle, we have delta S1 equals to R log V3 over V1 and delta S3 equals to R log V2 over V4. So the entropy change for the whole cycle is delta S1 plus delta S3 equals to R log V3 V2 over V1 V4. Substituting these results back gives delta S1 plus delta S3 equals to R log T2 over T1 to the power of 3 halves T1 over T2 to the power of 3 halves equals to R log 1 equals to 0. Thus entropy change is indeed 0 for a mole of monatomic ideal gas in the Carnot cycle. For non-Carnot cycle, we dissect it into many smaller Carnot cycles. Since the internal path cancel, entropy vanishes for an arbitrary cycle. This is again reminiscent of Green's theorem, which relates many little circulations to a big overall circulation. In fact, the cycle above can be regarded as a heat engine, which absorbs heat Q1 from hot bath at temperature T2 in process 1, dump this heat into the cold sink with temperature T1 in process 3, and outputs work minus W to the surroundings in a full cycle. We can define the efficiency of this ideal gas reversible heat engine as a ratio of work done on the surroundings and heat absorbed from hot bath in a cycle. And we denote efficiency with Greek letter eta. Thus, the efficiency is eta equals to minus W over Q1, which is Q over Q1, which is Q1 plus Q3 over Q1, equals to 1 plus Q3 over Q1. Then from the cycle we have 0 equals to the integral around this Carnot cycle, ds equals to Q1 over T2 plus Q3 over T1. And the slight rearrangement gives Q3 over Q1 equals to minus T1 over T2. Thus the efficiency of this Carnot heat engine is eta equals to 1 minus T1 over T2. So the engine has an efficiency of 100% if the cold sink is at absolute zero or the hot bath is at infinite temperature. Both are not practical. The heat engine has an efficiency of 0 if the cold sink and the hot bath is at the same temperature. The Carnot heat engine is the most efficient heat engine which is theoretically possible. This gives us a criterion for spontaneous change, but not a convenient one. The Clausius inequality contains d bar q, and heat is a path function. It depends on how the process is carried out, not merely on where the system begins and ends, and the clean statement ds is greater than or equal to 0 holds only for an isolated system, whereas nothing in a laboratory is isolated. So what we actually have is a flask held at a fixed temperature at either fixed volume or fixed pressure. In the next chapter, we rearrange the Clausius inequality to suit those conditions and obtain the free energies, which are state functions of the system alone, whose decrease marks a spontaneous change. They contain no new physics, they are the second law written in a form so we can take into the lab. See you in the next chapter. Thank you for watching.